Hello and welcome to the OpelX podcast. My name is Abhijit Kshirsagar. I'm a professor at the Indian Institute of Technology, Dharwad. With me on this podcast is my friend Dr. Lalit Patnaik, who works at CERN and is joining us from Geneva, Switzerland.
This podcast is a part of the Open Power Electronics Network, or OpelX for short. Come check it out at opelex.net. That's opelex.net. You can also follow us on Twitter. We are at OpelXNet.
The thoughts and opinions expressed on this podcast are of the respective individuals and not the organizations they are affiliated to. For more details, please visit the podcast webpage at opelex.net. That's opelex.net/podcast, or contact us via Twitter or email.
Hello everyone and welcome to a new episode of the OpelX podcast. Today we are interviewing Manoj Radhakrishna Iyer, who is an engineer at ISRO, that is the Indian Space Research Organization. He works at the ISRO Inertial Systems Unit in the power conditioning lab there. And Manoj and I used to be colleagues around 2011-2013 when Manoj was doing his Master of Technology there in Bangalore, India. So, hello Manoj.
Hi Lalit, how are you?
I'm good. How are you?
Yeah, I'm doing fine.
Nice. Yeah, it's been a while. We talked last time. So, maybe we will start with you introducing yourself in a more elaborate way. I just gave the keywords. You can just tell us more.
Yeah, thanks Lalit. So, as Lalit told, I'm working in ISRO Inertial Systems Unit, specifically on power conditioning lab and power supplies, to be specific. So, I kind of started off not exactly at the Inertial Systems Unit. I started off in Vikram Sarabhai Space Center. Back in 2005, I joined there and worked almost 3 years there, and then moved on to ISRO Satellite Center, Bangalore, wherein I worked on space grade power supplies. Then now back to the Inertial Systems Unit after completing my master's at Indian Institute of Science. So all along the work profile has been power electronics and mixed with a little bit of FPGA work once in a while. So that's it. That's more about the kind of work I do.
Nice. Very nice.
Okay.
So what are, let's say, some of the interesting projects you are working on right now in the power electronics domain?
Okay. Mainly my work has been focused around DC to DC converters and their miniaturization. Always a low swap, as they call it, swap C nowadays.
Oh, what is that?
Which stands for size, weight and power.
Okay.
And the C for the cost. So it's like meeting your requirements with minimizing all these. So that's the buzzword these days, swap C. And all variants come. Low powers, slightly high powers, low noise. You have to power sensors. You have to power acquisition systems. So it's a little bit challenging, I would say. So that's the challenge is what I enjoy.
Yeah. So when you say low power, what is the range of power levels that you typically have projects in?
Yeah, it can range anywhere from say 2 watts right up to say kilowatts sort of power levels.
Okay. Even kilowatts.
That's the range of power which I've been working on. Yeah. Yes.
So, hi Manoj.
Hi.
Good to talk to you again after many years now.
Oh, hi Abhijit. Same here.
So, can you talk a little bit about how you ended up doing power electronics for ISRO? So, when we think about space, we are thinking rockets, we are thinking aerodynamics, we are thinking, all sorts of aerospace and related applications, maybe something in communications, but power electronics is not necessarily something that comes to mind, right at the beginning or even at all. So can you talk a little bit about, first of all, how you got into the power electronics field at ISRO? Did you choose power electronics first, or did you choose ISRO first and then you ended up in power electronics?
Okay. An excellent question, Abhijit. In fact, I would go like this. As you said, when you say rockets, the first thing you think about is a lot of other stuff, controls, the computers, all those stuff. communication as well. So I ended up in power electronics because I chose ISRO first, Then I opted for like electronics design. And the power, to be frank, the power came into picture because of the, the BTech bachelor's project that I did, which was somewhat related to power, which was if you say power harmonic distortion measurement using MATLAB. So those days MATLAB, back in 2004 sort of time frame, MATLAB, we were just picking up, learning and all those. So that time, what I did for my project was, capture the power line signals, feed them to the laptops or computers, audio jack, audio port, line in port, and acquire that data and display it on a MATLAB in a graph. And when you operate a motor or something, how that harmonic distortion creeps in and how it corrupts the supply, all those. So that was my bachelor's project. So based on that, I think probably I got a posting in power electronics. And when I joined in, to be frank, I was not very, too much aware about the practical aspects of DC to DCs or power supplies, all those stuff. I basically learned it on the job, I would say. And so it's like that. But the moment since I started the job, I have been just loving it, learning it through the way, and it has become a passion. So
awesome. The other part is, what is when they brought you in and assigned you to a power electronics team?
Yes.
Of course, a lot of details are going to be proprietary and not public here. But whatever public information you can share, what are the kinds of problems that that space applications typically face when it comes to power electronics? Why can't we just slap in, let's say, a 5-volt converter from your phone or your anything else? Why not just take one from there and slap it on a spacecraft?
Okay, now there you are. So the typical environment that a spacecraft would experience is pretty much about the challenge part of it. Okay, the power supplies that we normally see around, like say your phone charger or your wall USB 5-volt 1 ampere sort of a stuff, these may not really perform to the way that you are looking at when they are subjected to, say, something like what I would say minus 40 degrees at one end, and probably plus 120 or so degree centigrade on the higher end. So that's where at that point too you should hold all your most of your specifications, except for obviously there might be some temperature drift. So all this stuff has to be held very tightly, even with such a wide temperature range. That probably is the challenge which comes with it. And of course the supplies have to be totally really clean, and the emissions part of it, that is another very stringent requirement on emissions.
Right.
As in, see, your wall adapter, it consumes far from your AC, and you might not be too much worried about the power quality, I guess. Not too high, as in when in a spacecraft or a rocket system, which typically works on DC bus. There are n number of systems connected in a DC bus, and nobody is supposed to almost send back anything back to the bus, because it's going to directly corrupt another system.
So you mentioned temperature, you mentioned EMI, EMC. I'm assuming just flat out reliability is also
radiation as well.
Oh, space radiation, of course.
Yes, reliability is another aspect, and radiation is, if you go to spacecraft, that is, as far as launch vehicles are concerned, it's a short duration, so it's not much of a challenge. But then when it comes to a spacecraft, it has to work for, even the spacecrafts work for like 15 years or above. So they have to be continuously on. There is absolutely no servicing, right? So it has to be on. So duration is one aspect of it. Surviving the environment is another aspect of it. Then the temperature variations, as in cycling, is another aspect of it. And vacuum, of course, is again another aspect of it. So there are multiple points to it. So you have very tight control over the materials that you should choose for going ahead with a vacuum environment. You should have the mode of conduction. When you say power electronics, thermal is another huge challenge.
Oh yeah.
If you have to handle power. Okay. So it's like you take a simple MOSFET or an IGBT, any device. Handling, I would say, 4 watts of dissipation in the single device is a challenge. Anything beyond that in a single device?
Yeah, because you don't have air. You can't slap a fan on it.
No, absolutely not. Absolutely not.
In space.
Okay. Conduction is the only mode.
Wow.
Conduction.
Yeah.
That's it. Yeah.
And maybe radiation.
Radiation, yeah. See, there you remember our Stefan's law, right? A is sigma T raised to 4. So when the temperature goes up, and when you have the area only, you get radiation. But practically, for power electronic or devices, you simply cannot depend on radiation. That has been our experience.
Basically, you need too high a temperature to be able to radiate enough amount of watts.
Precisely. That's the point. And so that's the issue.
So heating is also a problem, right? So when your spacecraft is facing the sun or is in sunlight, basically it's going to heat up fairly quickly, right? Is that also a concern?
True. Very much true. That's very true. But then that again is another totally different system. You have these thermal experts, thermal group. So they take care of all the spacecraft thermal management with the help of reflectors, radiators, and heaters on the other side when the spacecraft faces the cold environment. So that's a totally different challenge. They even do have heat pipes and all the other stuff. But then on a power device, on a package level, the challenge is taking away the heat and bringing them all to a point wherein it can be taken away as a subsystem, as in say base plate or base of your device or your package. So that's the challenge we face internally. So even that's a huge challenge.
So of course, one of the other big components is solar panels, right? Whenever we think of satellites or even the International Space Station, just visually the huge part of its physical structure is these huge solar panels.
Yes.
And I imagine there's a lot of power. I mean, all the power for the satellite or the station comes from the panels, and it's presumably being stored. So just managing all that power is another requirement, right?
Yes.
Reliably.
Yes. One is the first part. It starts off with extraction itself. So extracting the best out of these panels. That is one aspect of it. And then providing all this conditioned panel power to the loads as well as batteries. These days the loads come with quite high power demands. So not all the power can be supported by the panel also. So sometimes it's a combination of panel and battery which supports the load.
I see.
So even such scenarios exist. It depends on different applications or projects or the power levels that are involved. But typically, the energy from the solar panel, which normally a current source, as we say, is used for charging the battery as well as servicing the loads. And when the spacecraft is shadowed by the Earth's, a shadow when it goes towards what we call as eclipse, wherein the Earth comes in between the the sun as well as the satellite panels, where you don't generate anything from the panels, it has to be completely through the batteries. Supporting it. Right. Okay. So you have to even condition.
Yeah, that's really interesting.
Yeah. Even you have to condition the battery power because the battery voltage and the load demands do not always go together. And you can have just a common battery voltage and your loads will demand n number of voltages. So, and at different power levels, different noise levels, different current levels, that's wherein the power conditioning comes into play. So that's the crucial part of it. Maintaining whatever happens at your front end, maintaining a constant stuff at the other side.
Yes. I mean, you talked about such a wide variety of parts of the satellite where power electronics plays a crucial role. And I think sometime back we were having a discussion and you mentioned about how many of these technologies, though they are developed for space applications, are actually portable or transferable to terrestrial applications. And could you tell us a bit more about this aspect?
Yeah, definitely. See, the way I kind of see it is, if you take a satellite, you have these panels and almost everything runs out of it. That's almost what we are trying to now, I would say, replicate on ground here as well. Don't consume any other sort of power. Go ahead with only renewable energy, as in take out the energy from panel or the wind or the tidal, all those natural sources. renewable sources, and then convert all those or handle all these in a DC sort of an environment locally. So if you look at a house, today if I look at a house, if you have enough panels surrounding your house or rooftops, it can easily be converted almost similar, I would say, to a satellite power system. You have these panels, you have your storage batteries, and almost all your devices, the front end might be an AC to DC conversion, which happens, and then you consume the real power usage might be at DC, most likely. All right. So if you adopt these situations, I think it will be more efficient that way you use your power from your panels. And another application where I see very similar lines of work is electric vehicles. Even there, the system is battery based, though the panels are not yet fully into play. The battery aspect of it, as in a spacecraft being in an eclipse, I would say. You have all your batteries which are charged up, and you have to now efficiently handle this power to get your work done, which is moving about, right? So all this power conversion stuff, doing it at the peak efficiency part of it, keeping the size, mass, cost, etc., all the swap parts low. So that itself is, I would say, all these technologies are easily translatable to all our daily needs as well. And
so just to add one more thing, you mentioned space applications being translated to terrestrial. Of course, that's on a more long-term basis, I would think. But do you think that these translate to things like aerospace and aircraft and similar applications sooner?
Yes, of course. The technologies per se are actually, it's a two-way bridge, I would say. Any innovation you have here in these technologies are easily adaptable to a higher space sort of a platform, provided the reliability and all those stuff are established and you have the appropriate devices. But if you say you come up with a new topology or a methodology of doing something, which in similar applications, say in EV or so, it's easily adaptable to space technology as well. Okay, but aerospace, if you come to aerospace, again, the standards are slightly different because of the environments that they face, but not too different from a spacecraft or a space environment. Probably the radiation part of it might be not that much because it doesn't go to the outer space, too much beyond our Earth's periphery. So otherwise, aerospace is closer, as you said, but the ground or terrestrial applications becomes very challenging in cost aspect of it as well. The cost tends to take a little upper hand compared to the reliable part, and serviceability also comes into play.
Let me just touch on one thing you mentioned there, that cost is a challenge. I mean, of course, NASA and other space organizations have had the general perception is that they have truckloads of money, and then cost is not really a factor when you want to meet all these other requirements like reliability, performance, and all the other mission critical requirements. Cost is not a factor, but now we are seeing that change with NASA wanting to go with reusable rockets, bring down the cost per launch. And there are some companies that are sending up satellites which cost pennies, but relatively speaking, of course. But they don't last for 15 years. They may last, say, 6 months or 1 year. And the answer is to make multiple cheap satellites instead of having few very expensive satellites. So how do you think that plays into the traditional approach, which is to go all out in terms of reliability or something, and not have cost matter so much, whereas now where cost effective requirements are now becoming more prevalent, and that's going to be even more important, I guess, with commercial space flight and commercial launches becoming more mainstream, don't you think?
Yes, sure, definitely. You have touched the right chord as far as business is concerned, I would say. Okay, right. This is the way that the industry is looking at. Earlier, it used to be, the way we see it from inside, earlier it used to be like, you just do one design. Okay. one design, broad design, which almost fits most of the applications. And as you told, paramount importance was on reliability and other stuff. But now the focus is sort of, I would say, a much more custom sort of a point of view. As in, what does this particular application require? And how do I achieve it at the minimum most project cost or cost of ownership sort of number? Okay, so that's what we are looking at. Not the same, same shoes fits all sizes, or what they, as they say, not all, the same solution doesn't fit all the applications.
Okay.
So now we are having more focus towards applications and designing towards that. That's wherein the designer part or the designer's challenge comes in, as to understand a bit more regarding the application, and then you would be able to offer a better solution. So that sort of design practice is now coming into picture.
So Manoj, could you tell us some things about specific technical skills or even non-technical soft skills that you picked up over all these years at ISRO, which you think you might not have in many other contexts, and which you think are also transferable to other areas, and students could be interested in that, or young professionals?
Okay, specifically ISRO as well as the power field, the way what I have experienced is when you start working with something like power electronics, the manner in which or the way in which you see systems changes, your perspective changes. As in, I have worked in a little bit on the digital side as well. So I see it in such a way that if you look at power, you start imagining the origin of things, as in, how does something really start up, or to say, where does it get its source of power, and where does the power flow, and how does it flow, and who needs it, how much is needed. And when you look at all these stuff, you start understanding the system much better. That's what I have felt over the years. And another aspect of it is when you have to work on a power electronics field, you have to face or interface with almost everyone around, because nobody can work without power, right? So you start interacting with n number of teams. You start interacting with the digital team, you start interacting with the communication team, you start interacting with the thermal team, you start interacting with the mechanical, almost everyone. So ISRO is one platform wherein these interactions help, and you get to know a little more about the other systems. So it helps in your own personal growth, as well as you visualizing the whole system. So that's about the best thing that I think which I have acquired over the years. So that's one main part of it. And being in power electronics has helped me. Even had I been, my point was, had I been in, say, digital system also, my field would have been confined to that.
Right.
Okay. Like I may not know too much about communication system, or I may not too much know about analog electronics part of it. But then once you start going into the analog part of it or the power part of it, you see the other fields in a totally different way, I would say. In a totally different way. As in, from basic fundamentals, you start understanding the other fields as well. And it becomes very easy to pick up. That's what I have understood. The other fields. You become a fast learner.
Basically, the interface with so many other fields.
Yes. The interface, of course, with so many people, from different walks of life. So you tend to see other points of view as well, quite close. Okay, up and close. So that helps your own growth, I would say, from different perspectives. Yeah.
So Manoj, for young students or young engineers who are either just graduating now or about to graduate, what do you think are the key skills that an organization like ISRO is looking for when it comes to power electronics, or allied fields? What sort of skills are these organizations looking for? Is it a growing field, or is it shrinking? What's the scenario?
First, I would like to mention about the area. The area of power electronics is always there, and it has always been booming, I would say. Especially now with new sort of wide bandgap devices coming into the power electronics scenario. It's a totally different aspect of it, wherein you are going to take your power conditioning from, say, hundreds of kilohertz to megahertz range. So this is really another turning point, I would say, similar to the introduction of IGBTs probably for the higher power conditioning levels. Right. So now with gallium nitride specifically, it is a very exciting field, and a lot of new challenges as well come up with such devices. So the skill sets that one should look at is, I would say, the analog portion of it. If you have to enter into the power side of it, what you should be strong in is analog electronics and understanding how devices work. So that is very, very important. The power field is sustained, or I would say advanced, by devices. That is one major aspect of it. And of course the analog electronics design aspect of it, and magnetics. These are certain areas which I would say during my bachelor's period, I wouldn't say that I would have concentrated much into these. Analog, of course, circuit design, transistor based designs were there, but not too much into magnetics design, for example, or not too much based into what are the new devices that are around, like MOSFETs or silicon MOSFET, silicon carbide sort of devices presently. So these knowledge of devices is one aspect, and the knowledge of the analog electronics, strengthening it, as well as magnetics design. That is another very crucial aspect of it.
Right.
So such parts, I think we don't really stress in our curricula, at least while I was there at the bachelor's period. We did have a power electronics lab, but I think we had a specific set of experiments or stuff wherein we didn't go in depth into all these things. So so that is these are the skills I think would help an engineer grow in this field.
Yeah, Manoj, you have struck a really right point here about the devices, the focus on devices, which I completely agree with, especially from the point of view that if we don't understand the working of the specific devices and magnetics, as you mentioned, it doesn't matter how well we do with the control electronics, the converter will run hotter than expected, and that beats the whole purpose of power electronics.
Exactly, Lalit. And another aspect, okay, this is something I would say a little more personal. I don't know whether it's my experience or it's similar across all students. Back in bachelor's and all those stuff, at least I used to believe that it's the voltage that you should look at all the time, to know what is actually happening. But as and when I started my job, and slowly, I don't know, it was a wonderful device for me to first know, which is a current probe. Okay. This is something, to be very frank, I have not seen during my bachelor's. Okay. It's a bit costly device, true. But my feeling is all at the bachelor's level itself, we should start looking at the current waveforms. We rarely, we probably see them in textbooks. And personally, I never used to understand, okay, fine. Current is there, but ultimately it's the voltage supply that I turn on. Okay. And if the supply is still 5 volts, everything seems to be fine. But if it folds back, or if it turns off, something is wrong, something like that. Okay. But then after having worked a couple of years or so, what I would directly look for is, after turning on the supply, what's the current? Now it is drawing. That tells me everything. And what is the shape of it? That tells me everything. So it's like, I would say voltage is the cause, probably, the difference that you give, and current is the result. So if you want to know the result, we'll look at the currents. This is something I would give as an advice for maybe bachelors or such students. Start to look at current waveforms rather than voltages. Okay? Yeah.
Perfect. So, in your team, just switching gears a little bit, in your team, I'm sure you have a fairly sizable group there. Can you talk a little bit about what is your approach to solving research problems, design problems, and how you maintain innovation and out of the box thinking. Of course, it's a cliched term,
All right.
but how do you foster problem solving or creative problem solving or innovative design thinking, and especially bringing in some of the systems aspects that you had already touched on? How do you do it for your team, your students, or your employees?
Okay, contrary to popular belief, I think the way ISRO works is in small, strong teams. The engineer who is working on particular problem has the flexibility to suggest a new technology development in his own area. So it's more like a bottoms-up approach, I would say. So all these ideas coming right from the grassroots levels, they are allowed to be put into a common sort of a pool and then reviewed. All right. So that the best ones come up and they get funded. So that's how the research goes out. And the relevance of this particular technology, if you develop, how it affects the whole system will be taken up by a higher management, I would say. So that's how the development gets fostered. And towards problem solving, how we do it is almost like, I would say, divide and rule, I would say. Okay, so you break up your problem into specific small objectives or goals or tasks, and then distribute them to the person who is having a natural aptitude or a skill set towards that. And then you collect all this. There will be a common focal point, like say the team lead or the guy who does all this stuff, and he collects all these inputs from the different people to whom the small things have been assigned, puts them all together, and then tries to attack on the solution. So that's the way it is done. So small teams help in such things. Like there will be an expert in digital in one group, and the analog person will be another, and then there might be the person who might have a bit more magnetic skills to deal with. So that's how the teams pretty much work together. And as a subsystem, the solutions will be done mostly within the subsystem, so that it doesn't propagate to the next phase. And there will be, of course, special impetus once you have this all small teams, there will be specific and real focus on the interfaces. So the most of the time what we spent on, I would say, is on interfaces. So once that you get it cleared, that will be the one which will be fixed or frozen first. And once that route is clear, then everyone can go ahead working on their own jobs, right? So that's the way we work about.
Nice. I think that's something that other industries and other companies should really learn from. And of course, to some extent, the software industry is adopting some of these. They give it keywords like buzzwords like agile project management and
True.
So true. I think, but I think ISRO has been putting it into practice for a while now.
Yeah, very much. ISRO is a huge teamwork, I would say. Right. As in, putting all this together is really, I would say, and breaking it up. The system is what runs the whole thing, I would say. Right. Breaking up a complex task into simpler ones, that's the real beauty of it, I would say.
Perfect. And do you also engage with student teams, student projects? Does ISRO have some mechanism by which student satellites or student projects can also engage with ISRO? Is there some mechanism?
Yes, there are mechanisms. In fact, there have been a few satellites which have been launched also, built by universities. And ISRO regularly takes in project students, as I told you earlier, complex problems, you break it up into small stuff, and you even have small projects ready for students doing bachelor's or even master's. So such problems are also there. So ISRO regularly yearly it takes project students.
Excellent.
To complete all these small tasks.
Right.
So even that mechanism is around.
All right, then. Thank you, Manoj. Thanks for taking the time to talk to us. And we look forward to hearing more achievements from ISRO and from your group in the future.
I think you guys have almost covered a wide variety of questions and fields, and almost most of the things I had in mind, you have brought it out, I would say.
Thank you, Manoj, for this wide-ranging conversation we had, covering so many different aspects of power electronics and even beyond. And this was really enriching. And we would be happy to keep in touch with you about your future projects at ISRO. Thank you so much.
Okay, thank you, Lalit. I enjoyed a lot. I hope I could give something back to the community as well. Thanks, Abhijit.
The OpelX podcast is a part of the OpelX project. You can follow us on Twitter. We are at OpelXNet. You can email us at opelxpodcast@gmail.com for feedback, questions, comments, and suggestions. This podcast is hosted by me, Abhijit Kshirsagar, and Lalit Patnaik. Mixing and sound engineering is by Sudarshan Karthik, and additional support comes from Najat Abdul Aziz.